Relationship between the $th term and the sum. Welcome, everyone. Today we are going to explore a very important topic, the relationship between the nth term and the sum. Now, if you look back at our previous lessons, you'll remember that we spent quite a bit of time learning how to calculate the sum of the first n terms, which we denote as s sub n, for an arithmetic progression. In those lessons, we usually started with the basics, knowing the first term, which we call a, and the common difference, which we call d. However, mathematics often presents us with a bit of a twist. In many advanced problems, you won't be given the first term or the common difference directly. Instead, you might be handed a formula for the sum, s sub n, and then be asked to work backward to find a specific individual term, such as the nth term, which we write as a sub n. So, the goal of this session is to bridge that gap. We are going to dive into the logical and mathematical connection that exists between the cumulative sum of a series and its individual underlying terms. By the end of this, you'll see how easily you can move between the total sum and the specific values within the sequence. Conceptual understanding. Now that we've established that we are looking for a way to bridge the gap between a sum formula and an individual term, let's dive into the conceptual understanding of what these symbols actually mean. To understand this relationship, let us first define what $SN and SN1 represent. First, we have SN, which stands for the sum of the first n dollar terms. If we write this out, it is the first term, $1 sub 1, plus $1 sub 2, plus $1 sub 3, and so on, all the way up to the term $1 sub n minus 1, plus the $th term, $1 sub n. Next, we have SN1, which represents the sum of the first n minus 1 terms. When we expand this, we see it is the sum starting from $1 sub 1 through $1 sub 2, $1 sub 3, up to the term $1 sub n minus 1. If we look closely at these two expressions, you will notice something very important. SN is simply SN1 with one additional term added to it, and that specific term is the $th term, or $1 sub n. To make this even clearer, let's use a logical analogy. Imagine you have a piggy bank. If you know the total amount of money in the bank after 10 days, which we can call S sub 10, and you also know the total amount that was in the bank after 9 days, which is S sub 9, the amount you deposited specifically on the 10th day, which is $1 sub 10, is simply the difference between these two totals. This logic is exactly what we are going to use to derive our mathematical formula in the next slide. Mathematical derivation. Now that we have established the conceptual idea using our piggy bank analogy, let's translate that logic into a formal mathematical derivation. This is where we move from intuition to a concrete formula you can use in your exams. First, let's look at step 1. We start by writing out the full expression for the sum of n terms, which we call s sub n as we saw on the previous slide. This is the sum of all terms from the first term, a sub 1, all the way through the term before the last, a sub n minus 1, and finally adding the nth term, a very important piece, a sub n. In step 2, we can simplify this notation. Notice that the part inside the parentheses, the sum of all terms from the first up to the n minus 1 term, is exactly what we defined in the last slide as s sub n minus 1. So, we can substitute that whole group with the simpler symbol s sub n minus 1. This leaves us with a much cleaner equation. S sub n equals s sub n minus 1 plus a sub n. Finally, in step 3, our goal is to isolate the nth term, which is a sub n. To do this, we simply rearrange the equation by subtracting s sub n minus 1 from both sides. This gives us our fundamental formula. A sub n equals s sub n minus s sub n minus 1. This derivation is powerful because it provides us with a universal tool. As long as you are given a general expression for the sum of the terms, you now have the mathematical bridge needed to find any specific term in the sequence. We will put this formula into practice in the next slide with a real-world construction example. Real-world application example. imagine a construction company is stacking pipes in a conical shape. We are given a formula where the total number of pipes in the first n rows is represented by S sub n, which equals 2n squared plus 3n. The manager needs to find out exactly how many pipes are placed specifically in the fifth row, which we represent as a sub 5. To solve this, we will follow a clear step-by-step process. In step 1, we identify our known information. We have our sum formula, S sub n equals 2n squared plus 3n, and our objective is to find the value of the fifth term, a sub 5. In step 2, we need to calculate the total number of pipes in the first 5 rows, which is S sub 5. To do this, we substitute the number 5 into our formula, and this gives us 2 times 5 squared plus 3 times 5. Following the order of operations, we calculate 5 squared to get 25. So, we have 2 times 25 plus 15. This simplifies to 50 plus 15, giving us a total of 65 pipes. In step 3, we must find the total number of pipes in the first 4 rows, which is S sub 4. We substitute the number 4 into the formula. This gives us 2 times 4 squared plus 3 times 4. Calculating the square first, we get 2 times 16 plus 12. This results in 32 plus 12, which equals 44 pipes. Finally, in step 4, we apply the relationship formula we learned in the previous slides. To isolate the fifth row, we subtract the sum of the first 4 rows from the sum of the first 5 rows. Therefore, a sub 5 equals S sub 5 minus S sub 4. When we subtract 44 from 65, we get 21. Now that we have established the mathematical theory, let us see how this applies to a practical situation. Conclusion of real-world application example. So, to wrap up our practical example, after performing those subtractions, we arrive at our final answer. We can conclude that there are exactly 21 pipes placed in the fifth row. This confirms that by using the relationship between the sum and the individual terms, we were able to isolate the specific value for a single row, even though we were only originally given a formula for the cumulative total. Common mistakes to avoid. First, a very common mistake is confusing the nth term, which we call a sub n, with the sum of n terms, which we call S sub n. It is vital to remember the distinction. S sub n represents the cumulative total of everything added up so far, whereas a sub n is just a single, specific value at a particular position in the sequence. Don't let the two get mixed up in your calculations. Second, watch out for incorrect indexing. When you are using our formula to find a specific term, you must remember to subtract 1 from n to find the previous term's sum. For instance, if you are trying to find the 10th term, a sub 10, you must calculate the difference between S sub 10 and S sub 9. A frequent error is accidentally using S sub 10 and S sub 10, which would simply result in 0. Always ensure you are using the correct, decremented index for the second part of your subtraction. Finally, be extremely careful with calculation errors, especially when dealing with quadratic expressions. As we saw in our pipe stacking example, the formula for S sub n often contains an n squared term. This means you must strictly follow the order of operations, what we call BODMAS or PEMDAS. Always remember to square the value of n before you multiply it by any coefficients or add the remaining terms. A small slip in the order of operations here can throw off your entire result. Now, before we wrap up our lesson with the final summary, I want to pause and discuss some common pitfalls. Even if you understand the logic of the formula, it is very easy to make small errors that can lead to the wrong answer. Keep these points in mind, and you will be well on your way to mastering this topic. Key takeaways. First, remember that the nth term of any sequence can be found as long as you know the formula for the sum of the first n terms. This is a powerful tool because it allows you to move from a cumulative total back to individual values. The fundamental formula you must memorize is a sub n equals S sub n minus S sub n minus 1. As we saw in our derivation earlier, this subtraction is what isolates that single, specific term we are looking for. It is also important to note that this relationship is actually much broader than just arithmetic progressions. While we have been focusing on APs, This mathematical principle is valid for any sequence, whether it's arithmetic, geometric, or even more complex series. Finally, a very useful tip for your exams. If you ever need to find the very first term, which we call a sub 1, simply remember that S sub 1 equals a sub 1. This is because the sum of the first one term is, quite literally, just the first term itself. To wrap up our lesson today, let's review the key takeaways to ensure you have a solid grasp of this concept. Keep these points in mind, and you'll be well prepared to tackle any problem involving the relationship between terms and sums.